So let's get started. It's a real pleasure to have Nathan Wiebe here from University of Toronto. Nathan has been, as you probably know, he's done work very broadly and deeply in these subjects of quantum machine learning and as well as quantum simulation. So he's a great person to tell us about this topic of Barren Plateaus and quantum machine learning. So Nathan, as always.
Great. Thank you very much, Umesh. It's wonderful to be here. As always, I wish I could be here in person because Simon's is an absolutely amazing place to visit, but soon, I hope. In any case, so today I'm going to be talking about something that, has been a real passion of mine for quite some time, which is specifically trying to understand how we can practically learn in a quantum world. And this is, to me, the heart of the question of quantum machine learning. For, since the kind of the development of machine learning as well as information theory, we've begun to get a much better idea of what it means to learn pieces of information about physical systems. But many of the insights that we've developed over the last couple of years in the form of deep learning and neural networks, they don't really actually naturally map as cleanly as we would like over to the quantum world. And so what my main motivation for all of this work ultimately is I really would like to understand what it would mean for a quantum agent to learn based on quantum data. And a type of learning that we're going to be talking about here is a type of learning that people often don't talk about as much in machine learning, specifically generative learning. But the reason why we're going to be doing this is because of the promise that generative learning can offer under some circumstances to address issues of gradient decay that we end up seeing for this. And so let me just see. Okay, yeah. So the question is, though, from a practical level, what would we like to do in machine learning? Deep down, the way quantum machine learning usually ends up working practically, or at least for our current conception of how quantum neural networks work, we often view them as some kind of a parameterized unitary. Here I called it UNN of theta. And we have, for our system, a set of neurons. Now, these neurons correspond to a bunch of quantum bits. And what we would really like to be able to do is we'd like to be able to take some initial state and transform it with a parameterized unitary in order to get a final state, and choose those parameters in such a way so that when we measure a particular observable on that, we can extract some salient features from the state. And many of you might think, hey, wait a sec, doesn't this sound like exactly the same as VQE and QAOA? And the truth of the matter is, at this level, in terms of optimizing an objective function, it's very, very similar. And many of these problems that I'm going to be talking about involving gradient decay for these show up in exactly the same way across many different areas. However, I'm going to be focusing on QML applications in this talk. One of the things that I should mention is that there's a number of different ways, though, that we can solve this apart from necessarily just resorting to variational optimization for an objective that we're looking at. We can use standard quantum algorithms that have been developed for years, such as Grover search, linear systems algorithms, gradient descent algorithms, and the like, in order to be able to provide accelerations for these quantum algorithms. It should be mentioned that although many of these several of these algorithms in principle offer exponential speedups for these particular tasks, you've got to be very, very careful looking for exponential speedups for quantum machine learning tasks. And I would say for cases where there's classical data coming in, and we would like to use quantum machine learning to do this better, actually all of the techniques that I'm aware of right now only lead to polynomial speedups for those cases rather than exponential. And so the big question for me, given the fact that we really would like to see a huge speed up for any early application for quantum, is kind of, well, what sort of speed ups do we end up getting for these variational ideas, which often come with fewer complexity bounds than the rest of the algorithms that I discussed? And further, I guess the question is, what can we do for problems that are more situated in the quantum world, where we're trying to learn information directly about or from quantum states? And so the question, one of the key questions that we're going to be asking here is, could we use these particular ideas in order to be able to come up with ways of preparing quantum states that might be far more efficient than the naive methods that we would try to design by hand in order to prepare particular quantum states? So these are kind of some of the big hopes about it. And, just to give you an idea about how this works schematically, all of these algorithms end up working the same. What we do is we need to begin with some data that we would like to learn something about, or we'd like to classify. And so in order for us to kind of use a quantum computer in order to be able to do this, we need to map that data from whatever representation we start with to a state in the quantum computer. So, this is often done by some encoding transformation, which you can view in the classical side is even run by its own classical neural network that might compress the data into a small representation that we could then store in the quantum computer. Alternatively, if we have quantum data, in many cases, that data itself might be a quantum state. In those cases, a encoding transformation may not actually even be needed to load the data into your algorithm. However, you could consider trying to compress it using an idea like a quantum autoencoder or something similar to that. So once you've loaded your data in one way or another, you need to be able to train a classifier or get it in some particular way so we can map to a final state that when we measure an objective function will tell us how well we're actually learning about the data. And then our goal, at least in these types of machine learning algorithms that work very much like neural networks, is to optimize the parameters of this transformation in such a way as to maximize our objective function. All right, and that's basically the end of the game. Now, the question about how to optimize those parameters is kind of, well, it's a good one and it's a general one. The way that we often like thinking about this is in terms of gradient descent. And so this, however, many of the features that can make gradient descent expensive will make most other local optimizers that you take a look at expensive. So I'm going to be focusing this talk entirely upon gradient descent optimization for this, of course, recognizing the fact that there's other optimization strategies that could be used. So to give you the next question is, well, what would one of these quantum neural networks actually look like? That is one of these parameterized UNNs of theta. So here's an example of one from a paper that I did with Maria Schold now a fairly long time ago. But the basic idea behind it is that what we do, similar to an ordinary neural network, is we take all of our data, we encode it in quantum states, and then we have a series of controlled operations. So these G's, in this case, represent arbitrary single qubit rotations. So if you use an Euler angle decomposition, every one of the G's that you end up seeing in this decomposition would be given by 3 parameters. And so you can see that there's a fairly large number of parameters that we end up having in this particular quantum circuit. Now, just to give you an example of a classification task that we could try to solve for this, is we could say, all right, well, let's try to determine whether or not our state is from class 1 or class 0. So for example, we would have row 1 might be a mixed state that's of the form sum over all these phi j's over here. And row 0, which is a state that could be in class 0, would be a sum over all of these psi j's. And the basic idea is that we would have these two kind of distributions, which might be a uniform distribution over training examples. And what we would like to be able to do is, given an example that we don't know necessarily is a phi or a psi, we would like to be able to come up with a circuit that's capable with high probability of classifying between them. Although recognizing that in this context, the two vectors may not be orthogonal. So we may not actually be able to have unambiguous discrimination between the states in both of these classes. So what we would do in this particular case is we would, we would encode our data in such a way so that we have the label stored along with each of the vectors that we're considering for this particular case. And then what we would like to do is when we measure this top qubit over here, we'd like the measurement to match the label that we have associated with it. And so basically a natural objective function for us to optimize would be the average rate at which we end up getting the correct label coming back out of it. All right. So then we would just use gradient descent on all of these like 3n angles that we end up getting for all the g's that are in here and try to optimize it. So that's the basic idea of what this ends up looking like. Now, this leads to the big nightmare of quantum machine learning, which actually, ironically, comes from the greatest hope that we have from quantum machine learning. And that is that quantum states exist in very high dimensional spaces. And from that perspective, you can view a quantum computer as basically just a giant vector manipulator. But the problem is that that strength comes with the fact that this is a gigantic Hilbert space that we're operating in. And so something that ends up happening kind of generically is that you tend to actually get lost in high dimensional spaces. Or another way of putting it is high dimensional spaces tend to actually have some typicality properties. So for most functions on high dimensional spaces, or most well-behaved functions on high dimensional spaces, you tend to actually have what's known as a concentration of measure, meaning that most of the values that you evaluate these functions at tend to actually be concentrated about the same value. And so when we carry this out, the problem is that if we end up having this situation where there's a concentration of measure, nearly all initial parameters that we'll end up choosing for our guesses for these angles for the G's that we end up having in this circuit will yield to basically the same performance. And so this can lead to a problem because of the fact that if just about every configuration gives you the same value, then the gradients will tend to be very small, and in fact, exponentially small.
So Nathan, there's a question in the Q&A which says, well, beyond this sort of small gradients, why is it believed that the parameter optimization is a convex problem? Why could you not get stuck early?
Oh, it's it's not believed to be a convex problem whatsoever. So this is actually something that happens in machine learning as well, like for training neural networks. In practice, what ends up happening is when you train it, you do not ever find the local optima for training an ordinary neural network. Instead, you find yourself close to a local optima in practice every single time. And the idea, well, the thing that empirically tends to end up happening is that often the local optima that we end up finding tend to be good enough for people's purposes. So this raises another question, which is a fantastic one and a hard one, which is, in practice, if we're looking at the optimization landscape, are the local optima good for quantum classifiers, or are they actually really strongly suboptimal? And the truth is that we don't know. And also, we don't know, it's strongly believed from complexity theoretic arguments that it's not possible for us in general to be able to solve the global optimization problem. Otherwise, we would have BQPs and QMA in these, sorry, it is in QMA, but QMA is in BQP in these cases. So that's some of the reasons. So moral of the story is, yeah, we don't expect it's convex. And that's an open question about how much it impacts us. Cool. All right. So this effect that the gradients end up shrinking to some negligible scale, typically for these problems, leads to what's known as a Barren Plateau. Okay, so let me give you an idea about what a Barren Plateau is really kind of all about. The way I like thinking about it is, imagine that you've got a runner, okay, and the runner decides rather foolishly to go out running and near a cliff. The problem is that this runner in particular also happens to be blind. Okay, so the idea basically is that, the runner, in principle, when it's nice and flat, right, the runner wants to run really, really fast. And that's optimal until the runner ends up getting to the edge of the cliff. Sadly, if the runner is blind, then what'll happen if they're going quickly is they'll go crashing back down. And the analog of this, running towards a cliff problem is the exact same thing that ends up happening with the Barren Plateaus problem. It turns out that from the generic convergence proofs that we end up needing for gradient descent, we need to end up taking steps that are proportional to the inverse of the Lipschitz constant for the function that we're taking a look at. Or sorry, the Lipschitz constant of the gradient that we're taking a look at. So the gradient is nearly constant at first, right? Everything's nice and flat. So if this was our entire problem, just like the runner, we could take huge steps and it wouldn't really impact anything. The problem is that as we get towards the cliff, the derivative is changing discontinuously in the vicinity of the cliff. And so the Lipschitz constant that we need in order to make sure that the runner survives the potential fall down the cliff ends up leading to really tiny steps that we have to make everywhere. And we have to make that everywhere because the runner has no idea in practice when they're going to actually take a step at that and step over the edge of the cliff. And so this is the problem, is that if we've got a large Lipschitz constant for our derivative, but we end up in a region that locally has a tiny derivative, then gradient descent requires us to take a ton of tiny little steps, and it ends up taking an exponential time for us to navigate this barren plateau. There's methods that can be used in order to partially mitigate these problems, but for various reasons, many of them are either impractical to do on a quantum computer, such as evaluating the second derivative that you end up having for the runner going through, and others are also just they end up requiring too strong information about the landscape, such as knowing where the cliff is, or inexact solution, like giving the runner some momentum from the previous steps to help them carry through their gradients through regions of flat slope. So all of these problems are huge challenges for any gradient descent algorithm, and they are especially bad for quantum gradient descent. But to give you an idea about why these problems end up showing up, let me give you a toy example, which will give you the hint of why the objective functions tend to be flat for high dimensional spaces. Often, the kind of objective functions that we're looking at in quantum computing in these cases are problems where we want to be able to figure out what the overlap is between a current state that's generated by a quantum neural network and some kind of a target state. So, that ends up looking like the overlap of some phi and some psi squared. Now, let's assume that psi is a random state of the form given above, with angles going from θ1 to θ2 to the n. Okay, so we have all of these different components, and these values theta are chosen at random. If we average over all of those angles, we end up finding that the expected overlap between these two states is 1/2 to the n. However, if we go through the exact same calculation for the variance of that expectation value, we end up finding that the variance is 1/2 to the 3n, which means that the standard deviation is in order 1/2 to the 3n/2, which is vastly smaller than the mean. And this is something, again, that we could refer to as a concentration of measure. It means that virtually all of the examples that we take a look at, or virtually all of the psis, are going to have exponentially small overlap with the phi that we took a look at. If we only had the mean, then we could have some really fat tails where there might be a large fraction of the vectors that do have high reasonable overlap. But by bounding the variance like this, it guarantees that actually almost all randomly chosen vectors are nearly orthogonal. And this ends up leading to these situations where it causes, the expectation to be concentrated. Now, the problem of doing this outside, or I should say, this particular problem where we're looking at states that are of the form that I showed on a previous slide is actually just kind of looking at one slice of the total unit sphere that quantum states can sit in, or hypersphere, I should say, that quantum states would sit in a high dimensional space. In general, we need to actually do a similar argument, but over the entire space. And the way that we do this, rather than doing this simple integral over all of these angles, theta 1 through theta 2 to the n, is we need to do what's called a Haar average, where the Haar measure is basically the unitarily invariant measure over unitaries in an n-dimensional space. And that average that you end up taking a look at for it, it's also a lot more difficult practically to be able to do the integrals, because there isn't as nice parameterizations for it. So in practice, these integrals can be done, but symmetry arguments are usually used rather than an explicit integral like I showed you. And so for that reason, I wanted to show you the explicit integral to give you a spirit, the spirit of how these concentration arguments end up working. But the specific techniques for doing the Haar average are a little bit different than the ones that I mentioned before. So that is basically how this ends up working. And yeah, we end up finding, again, a concentration of measure for this when we do a Haar average as well. But getting back to machine learning, one of the things that we want to do is we really, again, want to maximize the objective function for this. We can end up talking about, well, what's the typical value of the objective function under the assumption that our neural network ends up giving a unitary that's typical of those that we would draw randomly from the Haar measure. Now, this question of typicality is kind of a good one. Like, is this an appropriate assumption to model our neural networks by a Haar random unitary? And it's somewhat debatable, actually. But in cases where you end up having a large number of purely random gates stacked together, random gates, as drawn from a universal set, tend to form at least what's known as an approximate two design. And what that ends up meaning is like at least the second moments of the distribution that you end up getting from random gates end up matching the distribution that you would end up expecting from a Haar random unitary. So that means that many of the characters that you would end up seeing from some totally arbitrary gate sequence end up actually matching those from the Haar random model. So it's often reasonable in these circumstances to try to understand how a totally randomly initialized quantum neural network would perform compared to the Haar measure. So if we end up taking that model for what a unitary neural network ends up looking like, we end up finding that our objective function ends up scaling like the like 1/2 to the n typically for these particular cases. I shouldn't have put an argmax there, but you get the idea. So basically, going through the exact same type of arguments about the variance as well, we end up finding with probability 1 over virtually all the random initializations that we would get under this Haar random model, ends up leading us to quantum neural networks that predict virtually nothing. So it says almost all random initializations for quantum neural networks are next to useless. So, okay, great, but the question is, can gradients end up saving us? Because all we ended up showing before, or that argument ends up leading to before, is that the concentration of good parameters for neural networks is incredibly low. But that doesn't necessarily mean that the bad parameters for neural networks aren't immediately adjacent to good neural networks. And in those cases, gradient descent might actually save the day. But it turns out, unfortunately, generically, we don't expect this to be true. But in order to show this, we need to kind of make a little bit more of a more special assumptions about the functional form of our quantum neural network to do this. So the standard assumption that's used is that we end up assuming that our quantum neural network ends up taking the form of a product of a bunch of exponentials of Hamiltonians, with a number of theta j's being our individual parameters for these. So as you can see, the previous case where we were dealing with single qubit rotations and controlled single qubit rotations, we can view each of those as having a decomposition in terms of exponentials of Hamiltonians, like this form over here. So this is relatively generic. So if we end up assuming that we have an ansatz like this, then we can actually go through and compute the derivative of this ansatz with respect to one of the parameters. And just by using the product rule over this, we end up getting the following expression here for the derivative, which basically ends up looking like the Hamiltonian corresponding to that parameter we're differentiating respect to, conjugated by a bunch of those unitaries over here. Now, at this point, we've got now like two unitaries that end up coming in. We end up basically getting a V unitary as well as a W unitary, and we've got the U of theta unitary. Let's now go through and model all of those as being Haar random unitaries. If we go and do that, then we end up finding the derivative of this is equal to this expectation value, this result over here. And going through the Haar averaging of this leads to the result that for all but an exponentially small fraction of the parameters that we end up picking in this case, we end up seeing that the expectation value of our observable is exponentially small, or our gradient is exponentially small. So this ends up meaning that basically gradients typically, if this Haar random model ends up being appropriate, which it often is, then actually gradient descent will not be enough in order to get us away from this Barren Plateau situation I was talking about previously, where we have extremely small gradients going up before we end up hitting a regime where we can finally start making progress in our objective function. So this is a major, major problem conceptually, right? How do we deal with these problems of having tiny gradients in this? Now, the answer is, well, classically, one of the things that we can get by with is we can get by with the fact that we have access to high precision arithmetic. If we need to have 16 digits of accuracy when it comes to our gradient calculations, for most classical algorithms, at least most deterministic classical algorithms, that isn't a problem. We can compute to double precision, just using ordinary arithmetic. However, for quantum neural networks, if we wanted to be able to compute the gradient of a function of the type that we were talking about before, which would be something like an expectation value of an observable, we end up finding that under the assumption that our function is this from the special class known as a Jevry class, then the number of operations that were accesses to this function that we would need in order to be able to evaluate the gradient is lower bounded by something that scales like 1/epsilon. Okay, so if that means our gradient is like 10 to the minus 16, the value of epsilon that we would end up needing in order to just even get the sign of the gradient correctly is about 10 to the minus 16, which means that the number of steps that we end up needing would be like 10 to the 16 in order to be able to evaluate even just the direction that we're taking for the gradient. And so this ends up meaning that for the tiny gradients that can sometimes show up for deterministic classical neural networks, the number of steps that we would need in a quantum neural network is truly frightening in order for us to be able to evaluate these gradients. And so this is a way in which the tiny gradients that you're seeing end up turning into a vast number of operations that we end up needing for a quantum computer to be able to kind of bushwhack its way out of the Barren Plateaus that we expect it to generically find us in. So this is why this is a horrible problem. So again, the problem is from two aspects, right? If we want to be able to try to tackle this, perhaps the first way that we could deal with this is try to inject prior information. Because I said previously that the typical configuration of those angles ends up giving you a really bad performance. If you have some insight about what good angles are before you end up starting, this can actually potentially sidestep the problem entirely, because your unitary may not be one that's typical of a Haar random unitary. And thus all of the arguments which hold for typical Haar random unitaries won't hold for your case. This is a big saving grace for applications to these ideas in chemistry, for example, where we'll often begin with something like a mean field approximation to the ground state that can be found classically easily. And that means that these arguments are less scary in that setting. However, for quantum machine learning, it's often a lot more difficult to be able to impose some prior knowledge about what the structure of the classes are that you're trying to learn for the underlying data. And so this task of navigating the space is a lot more difficult. So one avenue, and the avenue that I'm going to be talking about through the rest of this approach, is to actually kind of flip the script. In order to, instead of looking at, classification as a standard problem in quantum machine learning, I want to ask, well, do these vanishing gradient problems show up in precisely the same way for generative tasks? So in particular, can we end up, and this raises the question, can we learn to generate something like this mean field state? Can we, carry out some type of a protocol and find some approximate state that mimics closely enough some training distribution that we end up having, and use that as an initial atypical starting point for the algorithms from which we can learn and potentially sidestep these concerns that the Haar averages that I discussed previously end up raising. And so, and this again raises the bigger question is, are generative objective functions also just as prone to Barren plateaus as the discriminative ones, like the average success probability of a classifier? Okay, so just to give you an idea about what quantum generative training would end up looking like is the following. What we really would like to do is we'd really like to be able to, say, feed in copies of some particular quantum state. And the simplest one is just one quantum state being fed in, right? And what we would like to really be able to do is we really would like to be able to output some quantum state such that some kind of a distance, and that choice of distance is entirely up to you. That type of distance between the state that's output by the generative model is small with respect to the states that it's trained with. Okay, so that's the basic idea behind it. And if we basically end up feeding this in, let's see, if we basically end up having a situation where we're not just feeding in a single state, but instead we're feeding in a conditional state, we can also think about that in the exact same language. But what we really need to do is we need to consider an expectation value over all of the distinct states that are fed into it. So that's basically how you can end up generating not just a state, but also generating a family of particular states using this type of an idea. But a lot of the art behind all of this ends up boiling down to your choice of distance metric for this. There's a number that you could end up picking, but the one that I really like is I like relative entropy for reasons that I'll get into for a while, shortly. But another thing that I thought might end up helping the discussion is to make it a little more concrete. Rather than us talking about generating like an arbitrary quantum state, I'd like to focus on a particularly important family of quantum states. In particular, I'd like us to talk about generating what are known as Gibbs states. The idea behind a Gibbs state is a Gibbs state ends up describing the distribution that a quantum system would be in if it's allowed to equilibrate at finite temperature. And so basically, this distribution is given by this matrix sigma I stated on the left, which is e to the minus h over some quantity known as a partition function, which is its trace. So think about that z. It's just some constant that you need in order to normalize e to the minus h to be a proper density matrix. So that's the basic idea behind it. And what we would like to be able to do is we would like to be able to build a quantum neural network that contains both visible as well as some qubits that are hidden, as in they're just latent qubits that are used to generate correlations, but not directly observed by the end user. And we'd like to be able to trace over those hidden variables of the output state and have that resultant state after the trace be as close as possible with respect to your favorite distance to the Gibbs state that we'd want to generate. And so from that perspective, once we found that, then our parameterized unitary or quantum neural network can be thought of as building a purification to the Gibbs state, or at least an approximate purification of the Gibbs state. So that's the idea. And so there's good reason why I ended up picking it, a Gibbs state in particular, which we'll see in a moment. But let's talk about some of my favorite distance measure for this. My favorite distance measure to take a look at the distance between two quantum states is the quantum relative entropy. For those of you who've spent some time with machine learning, the quantum relative entropy is a analog to the KL-divergence between two probability distributions, which is known and loved in machine learning circles. It's basically defined here as the von Neumann entropy of the state on the left minus the cross entropy between the two, which is the trace rho log sigma. And this particular result is really important for hypothesis testing. You can end up bounding the error that you end up making in hypothesis testing between distinguishing between two quantum states, rho and sigma, in terms of the number of copies that you end up feeding into the optimal discriminating circuit and the relative entropy between the two states that you're trying to identify. So it's really, that's one of the things that I really like about it. It has a well-motivated information theoretic basis for it. It's got one other property that's kind of like a mixed bag, and that is just like the KL divergence, it's asymmetric. The quantum relative entropy between rho and sigma is not the same as the quantum relative entropy between sigma and rho. They've got slightly different interpretations, and that's why it's not symmetric. But the key thing is that the double-edged sword about this is that you can also pick the order of the divergence that you're taking a look at to end up matching your computational needs. Sometimes one order, we'll see, is vastly easier than the other order from the perspective of computing gradients. So, my collaborators and I use that trick frequently in order to be able to make models that are easier to train with respect to one direction of the relative entropy than the other. But one thing that ends up coming up is that it's often kind of difficult for us to be able to optimize this function. One of the main reasons why is that it involves matrix logarithms. And so we've got to differentiate matrix logarithms. Now, that's a little bit difficult because of the fact that when you differentiate an operator, right, you normally end up, you often like to use the chain rule. So say you have something like this, right? You might say, oh, this is just equal to G prime of f prime of g of x, something like that. So you can't use the chain rule. One of the things that fundamentally is used in a derivation of the chain rule is you use in its derivation the fact that functions commute with each other. So however, we're differentiating a matrix function. And so the derivative of the matrix logarithm that we end up seeing over here isn't something that actually works for the chain rule. So we have to use very, very cumbersome expressions in those cases to be able to differentiate it. And so that's why, even though it's my favorite metric to try to optimize, we don't often do it in practice. And in practice, what we'll often do is the much easier Rényi 2 divergence. The Rényi 2 divergence is this trace rho squared sigma inverse function. It's known to be an upper bound on the quantum relative entropy and also ends up satisfying that the Rényi divergence, when you're looking at the Rényi divergence between two states, is equal to the quantum relative entropy is equal to 0 if those two states are the same. So this ends up leading to a situation where we're trying to optimize a function like this. We really would like to make D go to 0, okay, which would be like the relative entropy in our case. But if we can get the Rényi divergence to go to 0, because it's an upper bound, and it's a tight upper bound near 0, pushing the blue curve to 0 also guarantees that the red curve goes to 0. So this is one of the reasons why, although it's not as good as optimizing the quantum relative entropy directly, it's the next best thing, and it's vastly easier to optimize because of the lack of matrix logarithms. And you can see that because it's the logarithm of the trace here, not the trace of the logarithm. So this is just an ordinary logarithm that we can differentiate using ordinary rules of calculus. Okay, so yeah.
Sorry, there's a question in the chat. So Rishi says that they got a bit lost in between. The question is, am I correct in understanding? Oh my goodness.
So Nathan, do you see the question in the Q&A?
Oh, no, I don't.
Okay.
Oh, the question is, yeah, so do the popular variational algorithms like BQ and QAO also suffer from Barren Plateaus? And then the other question was about, for QAOA, there's some results about how for random instances, maybe you can extrapolate from a small instance to a bigger instance. And what do you think about the general utility of this strategy?
Yeah, I think these are all things that potentially sidestep these arguments over here. The problem of vanishing gradients, regardless of your approach, that's always something you have to worry about. It could show up even for the best use of prior knowledge and the best choice of objective function that you're taking a look at. However, whether it's typical or not for these cases where you're extrapolating up in QAOA, or cases like quantum chemistry where you're approaching the problem with a lot of prior knowledge, it's really we really don't have reason to believe that these Barren Plateaus are necessarily typical. But you still could find yourself in one. So it's perhaps good to walk out with your machete, but you may not necessarily need to worry about drop bears. So in any case, I just wanted to go through and show why actually looking at Gibbs states is so awesome for the Rényi 2 divergence. So the reason why it's so awesome is, take a look at this, right? The distance between the two states is the trace of rho squared sigma inverse. Now, sigma inverse, it's a pain to compute normally. If you take a look at our full paper on this, we show a polynomial method that you can use that was used in some LCU based approaches to linear systems algorithms. But we can use that in order to approximate sigma inverse to do this for generic state. It's cumbersome and it's expensive. But actually, for Gibbs states, sigma inverse is trivial to express because sigma is e to the minus h over z. So sigma inverse is just z times e to the h. Furthermore, for the case of the Gibbs state, you're told what the Hamiltonian is to begin with. So what you can do is you can actually just take the expression for the derivative, and I skipped a bunch of steps over here. Trust me, this is the derivative of the Rényi divergence. And then these exponentials of the Hamiltonian, we can then Taylor expand those out to an arbitrary order. We then truncate the Taylor series in the numerator and denominator, and the entire problem boils down to computing these expectation values of different powers of the Hamiltonian multiplied by at least 2 density matrices. And so then what we need to do in order to be able to estimate this is that we need to be able to basically estimate both the numerator and denominator with insufficient error in order to make sure that the error propagates to epsilon over the entire result. And we do that essentially just by either using sampling or, because I'm nerdy like this, amplitude estimation.
Nathan?
Yeah.
So this is where I get nervous when I see the trace, when I see the rho squared, and then combine that with sampling. So should we be scared here, or what?
Sometimes
yes.
Is it
good or bad? Oh, okay, you'll get more parameters.
Yeah. So sometimes you should definitely be scared. This is not always going to end up working. And you know that this isn't always going to work because if we were able to always be able to say variationally train a unitary that could prepare a low temperature Gibbs state, then we'd be able to actually show that QMA lies in BQP. So there's got to be some barriers where the efficiency is just going to break down completely. However, it doesn't break down in all scenarios. So going through
Can I ask a quick related question?
Yeah, Brian.
Hi, nice talk so far. So if you had told me, oh, go prepare a Gibbs state, and I was just thinking with my physics hat on, I would have said, oh, ETH, let me just go ahead and do time dynamics for a little while, and under time dynamics of that Hamiltonian, I'd expect to get a Gibbs state as long as I can start with something reasonable. And I look at your formulas, and they don't quite look like thermodynamics, but I mean, they have a flavor of sort of sneakily doing time dynamics. Is there any relation here, or is this just totally different things?
Well, the type of approach that I'm using here is kind of a little bit different than using some ETH-like argument, because I feel embarrassed talking about this because I've only dabbled in quantum thermodynamics compared to experts like Aram and others. But one thing that, at least as far as when I looked at the literature, that really you needed to worry about is you really need to worry about all these issues of windowing, and it was necessary sometimes to make strong assumptions about the form of the Hamiltonian to guarantee convergence to the Gibbs state. So the nice thing about this type of an approach is that we can guarantee that we're going to be with an epsilon error of the Gibbs state with certain computational resources. I would say
that makes sense to me. Is there any relation, or is this just a totally different approach?
I think they're kind of different. I'm not seeing any clear relation at the moment. Perhaps actually, something that could be done is if you wanted to think about maybe a physics-inspired form of a neural network for carrying this out, it might be possible to get some advantages over a completely random Hamiltonian sequence if you take advantage of insights from quantum thermodynamics. But I haven't put too much thought into it.
Great, thanks.
I would say actually probably the method that's closest to doing this would be kind of preparing Gibbs states using quantum analogues of Metropolis Hastings algorithms. Those feel to me like they've got the closest analog to a physical process, because it's very much like a physical annealing process that you would carry out.
Okay, thank you.
No problem. But in any case, for going through and computing those expectation values, you need to compute expectation values of multiple Hamiltonian terms, which we've assumed are unitary in the previous discussion. And we also need multiple density operators. So how do you do that? It feels like you need something kind of like the swap test, but you also need something kind of like the Hadamard test to be able to pull it off. So we ended up inventing this thing that I originally called the Swapamard test, but sadly my co-authors didn't like that name so much, and I understand it's horribly annoying. So we decided to call it a generalized swap test instead, which does exactly that. It'll compute an arbitrary polynomial of expectation values and density operators that we feel like. And all of the terms that we ended up getting in a previous expression are exactly of that form. So we can just run this circuit in order for us to be able to estimate each of the quantities at hand with an epsilon error. Of course, going back to Aram's question, the question is, all right, well, how small does that epsilon really need to be in order to make sure that a small error in the numerator doesn't propagate into something giant when divided by a tiny denominator? And so that is a good question. And I won't bore you all with all the details about the complexity of this, but if here's the final result for the complexity of using gradient descent, assuming that we've got a gradient with a function that has a gradient that's Lipschitz continuous with Lipschitz constant lambda, then the final expression that we end up getting for the complexity ends up scaling like this, where epsilon is our desired error in the end. So everything that we end up getting in this ends up depending kind of on the ratio of this e to the 1 norm of the coefficients of the Hamiltonian divided by this other junk over here. So in the event that the trace of the exponential of the Hamiltonian relative to this junk at the top is actually order 1, then we end up getting into a situation where we can efficiently, using this method, estimate, go through the entire gradient optimization process. And so this ends up meaning that, yeah, if we're looking at a high temperature Gibbs state, we can do this. But we can't do this in general. So that is that's basically kind of the situation where we can carry this out. And it works extremely well in practice, though. When we actually end up taking a look at this, we ended up seeing that we can train a quantum neural network to end up building a arbitrary thermal state. And the other thing that's actually really kind of neat about this is that the quality of the prediction actually ended up getting better systematically as we provided more and more hidden units to our quantum neural network. Previously, work that my collaborators and I had done showed that often hidden units are kind of a nightmare scenario for neural networks, that the extra entanglement will end up actually causing you to effectively decohere and the predictive power of your neural network dying. And this is the first time that I've seen actually big improvements coming out of a training scheme that actually uses neural networks because of the use of this different objective function. So this works really well for learning states. Furthermore, when we can actually go through this and take a look at whether or not Barren Plateaus end up existing for this training objective function in general. So this part over here, I'm not specifically just talking about Gibbs states. I'm talking about the general objective function, which is the Rényi divergence between the two. When we take a look at the gradient of it and actually end up computing the expectation value over the Haar measure, we end up finding that a lower bound on the expected square of the derivative of the Rényi divergence is given by this mess over here. So just like Aaron was saying, there are some circumstances where this is miserable, right? Like, for example, if we end up taking a look at the case where norm sigma is 1, then this whole thing ends up going like 1 over 2 to the 2n, roughly speaking. Actually, I guess the trace might be a little bit better than that, but roughly speaking, it could be as bad as 1 over 2 to the 2n. Vincent, you've got a question?
Yes, hi. I was wondering about the previous slide where you showed that the training is better with a higher number of hidden units.
Yeah.
And I was curious what the dimension of the Gibbs state you were trying to prepare was.
Oh gosh, I didn't put it here. I believe that it was a 4-qubit Gibbs state plus, a number of extra hidden qubits equal to the number of hidden units over here. So it's anywhere between 4 and 7 qubits that we were looking at.
Right. Okay. So it didn't have to be greater than the dimension of the target state. That's interesting.
No.
Yeah. Cool. Thanks.
Ehud, you got a question?
Yes. Yeah. Sorry. So I'm wondering if you're not comparing really orange to apples by comparing the Barren Plateau in the discriminative algorithm compared to this, because now what you are comparing at the output is this KL-divergence of your output state, which in itself will require an exponentially large number of measurements in order to measure that number.
Beautiful question, Ehud. Yes, this is one of the things that I really like about this objective function. The relative entropy is very difficult to be able to estimate directly. But actually, its gradients aren't bad at all. Mm-hmm. So this is something that actually ended up also showing up in ordinary machine learning with the KL-divergence. The KL-divergence is hard to estimate, but the gradients of the KL-divergence often can be estimated by statistical sampling. So we end up in a similar situation here. Under circumstances where the complexity of the gradient evaluation is reasonable, which happens in some cases, then we can actually optimize the relative entropy. But finding the value of the relative entropy at the end of it may still be exponentially hard.
Mm-hmm. I see. I'm okay. Maybe I can ask at the end, but I'm wondering how computing the gradients is easy. Maybe.
Okay, I can try that really quick. It's not necessarily easy,
Yeah.
but it's basically the reason why is that the gradients end up taking a form of some type of a function that ends up looking like this. For the generic case, that isn't a Gibbs state, we end up having polynomial expansions from a polynomial expansion of the inverse of the second operation. But it spiritually ends up looking the same. That what we've got to do is we've got to take a expectation value of a bunch of density operators sandwiched between a bunch of different Hamiltonian terms. And that's something that we can evaluate using this circuit. And so then it just really boils down to what these ratios are. And the ratios aren't necessarily horrible. They can be in some cases, but they're not necessarily horrible. Kind of like, learning the partition function more or less is almost necessarily horrible.
Okay.
So, okay, key point, I know I'm running low on time, is that in this particular case, if we're dealing with a situation where the norm of sigma is like 1, that's kind of like this nightmare situation that Aram was referring to. And the lower bounds that we can prove don't necessarily end up precluding that we have a Barren plateau. However, in the case where the norm of sigma is exponentially small, which is a case where our states are very high temperature and very distributed, then actually these lower bounds end up giving a value that's kind of on the order of 1. And this ends up showing that the Barren plateaus that we end up seeing generically for most of the discriminative training objectives that have been considered so far don't necessarily need to apply for generative objective functions like the quantum relative entropy or the Rényi divergence. And in part, a lot of this ends up coming into here from the fact that when you take a derivative of a logarithm, you automatically kind of normalize the derivative. If something's small on the numerator, it ends up being paired with something small in the denominator. And that, under certain circumstances, can actually save the day when it comes to the expectation. So the question is, all right, this part of the talk is a little more speculative. It goes to this question of, can we end up finding a generative pre-training algorithm? Can we use this generative training over here as an initial step towards building a better classifier by using this in order to get us outside of a Barren plateau? And this idea can work quite well. In fact, actually, it was used all the time with training of classical Boltzmann machines because they suffered from horrible gradient decay problems when looking at discriminative training objectives often. And so you would typically begin with a generative phase where you would try to generate the training data and then finish it off with a ordinary, like, looking at the average success probability of the classifier step. And so this ends up kind of boiling down to a question, well, can we do this? Well, a way that we can do this is we can try to find a Hamiltonian for the data using the previous methods that we took a look at. So by doing the Gibbs state optimization, but in reverse, where we take the derivative of the Hamiltonian parameters to try to match some training data, we can find a thermal state that actually does a pretty good job of representing the training data that ends up coming into it. And so once we've done that, what we can do is we can then say, okay, we've got a Hamiltonian. Let's then add a penalty term to our particular Hamiltonian that ends up coming in. And that will end up making our thermal state concentrated on the particular state that you would like to try to classify. So we put a penalty in order to be able to make that state much more likely in the distribution that ends up coming out. Then we use a Gibbs preparation method in order to be able to do this. That Gibbs preparation method could be a number of different ideas. We could try to use an ETH idea like Brian ended up suggesting. We could use a Metropolis-Hastings type approach, or we could even use the methods, variational methods I was talking about here. In any case, what we do then is we use that in order to generate an initial state. And then we finish it off with a VQE-like optimization over the quantum neural network once we've input that into our system. So we can use this kind of like a pre-processing step in order to take our initial state into something that is close enough to the correct distribution that we would like over the labels, so that ordinary training can finish it up.
Nathan, in that first equation, are all those letters what they should be?
Oh, no, the H, sorry, last minute change. The H should be an alpha.
And the U's are U's.
The U's are the Hamiltonian coefficients. So I might have called them H previously. I thought I fixed that. Oh, darn, I missed that. This is what happened.
But they're like the local polyterms or something.
Yeah. Exactly. They're like local polys. But so in any case, this is the idea for it. And then those are the different parts of the optimization process that would be handled by these steps. And when you go through it, the cost of this whole protocol ends up scaling like this, where capital lambda is the Lipschitz constant, L is, the number of terms that you end up having, N is the number of neurons in your system, and the rest of it end up depending on kind of the properties of the Gibbs state that you're trying to prepare. So basically, okay, to conclude, Barren Plateaus can be a real challenge when it comes to quantum machine learning. And I think it's fair to say that we don't have a universal solution for Barren Plateaus in general. And they're especially pernicious for quantum neural networks because the gradient is only learned by sampling. We can't rely on double precision arithmetic to end up giving us a high number of digits of accuracy for our gradient at low cost. And furthermore, we ended up seeing that generative objective functions like this relative entropy are not necessarily as prone to Barren Plateaus, although they can show up under certain circumstances. And in order for us to really, despite the fact that Barren Plateaus aren't generically appearing, such as in this analysis that I alluded to here, we need to consider the fact very carefully that the result that we end up taking a look at is a ratio of two numbers. And so we need to consider the computational costs of estimating everything within epsilon error. Because one of the dangers, if you don't pay attention to computational complexity, is you may find that you've got an objective function that there's no Barren Plateaus for, but it may be exponentially hard to evaluate. In that case, sure, you solve one problem, but at the price of the other. So one of the things that I really strongly want to advocate for, that I think more people in the machine learning community really need to do, is it's not enough, I feel, to just take a look at gradients and take a look at how well the fully trained model ends up performing. We really need to consider what the computational complexity of absolutely every step going into it is, because you can make these trade-offs, right, where your gradients end up getting a lot better at the expense of the computational complexity, and potentially vice versa. However, under certain circumstances for high temperature Gibbs states, the methods that we prepare give a good way for you to be able to generatively learn those particular states. And furthermore, kind of more tentatively, this might provide us an avenue that we could use in order to, in some cases, escape from the Barren Plateau problems that we've seen in QML by generatively pre-training our initial data to kind of make a wormhole between the bad space in the optimization landscape and the good space that's close to the solution that we'd like to be. And this might actually end up becoming an important strategy in our fight to try to finally build practical quantum neural networks. Thank you very much.
Great, thanks a lot. Yeah, that was great. Let's see if there have been plenty of questions. If there's a burning question, please go ahead and ask now. Otherwise, we'll move on to the panel. And Nathan, if you stop sharing, then maybe
sure, no problem.
You can start pinning up the video for the panel. Okay, so let's see.